Hello everyone. In the last video, we came up with a methodology where we split the load at this particular node into two halves, and where each half was driving us a pair of flops. So see, similar thing happened over here. The advantage that we had by using this particular methodology was that now the waveform that you expect at the clock pin of the flop at the flop endpoint is exactly similar to the one that we sent at the input. So that is the clear advantage of breaking up the or splitting up the loads at this particular node. Else the transition, as we saw, it was very bad at this particular node if we didn't had these buffers. So that was one of the clear advantage of having or of splitting the loads at this particular node. And now what we'll be doing is but there is again a penalty over here. So the penalty is the area penalty. So you need two extra buffers to be placed over here. So you need some amount of area that has to be spent on the chip area. So that is a part of the chip area, and obviously we have to pay some amount of cost for that area. So again, we have got a very good waveform at the clock pin of the flop at the cost of an area penalty. So that is required, and that particular penalty is the one that we can't avoid. So we have to stay with it, but we have to also make sure that we don't over design our circuit. By over design, I mean we should not be using too many buffers in this area, so that it will clutter over here and there will be some extra area that gets occupied. We should be using the number of buffers that we should be using should be what is required. It should not be more, it should not be less. So we'll be getting into this topic also in the later sections of the videos. So now what we'll do is, so this was the clock tree that we had built over here. So let us try to deduce some important observations out of this clock tree. So let us try to do that first. So the first observation over here is, so if you see, whenever there is a waveform that is present at the input of this particular buffer, it will cross this and reach over here at the output of this buffer. So whenever a waveform crosses from one area to other area, we call it as a level. We call that particular thing as a level of buffering. So this is the first level of buffering. Again, from this node, when it reaches to node B or node C, it again crosses this particular barrier and it reaches this particular area. So this thing will be called as second level of buffering. So what we observe over here is there are two levels of buffering in our clock tree. In this particular clock tree that we are seeing, there are two levels of buffering. So each level, so there is a way to define it. It's like each level can have n number of buffers, but the level definition will be same for those all n number of buffers. So whenever a signal crosses one buffer, that will be called as one level of buffering. In this case, there are four levels of buffering. For example, this particular signal crosses this buffer, so this is the first level. When this particular signal reaches here and crosses this buffer, this will be the second level. Similarly, when it crosses this particular buffer and reaches over here, that will be the third level. And from here it reaches this and this point simultaneously. So this will be the fourth level of buffering. So in this tree we have four levels of buffering. In this thing we have got two levels of buffering. So that is basically the definition of when we say levels of buffering. So this has got two level of buffering, this has got four level of buffering. So the first and foremost observation that we have is that in this particular clock tree, it has got two levels of buffering. Okay, it is important to know what is the level of buffering. So for some reasons that we'll be looking in later sections. So right now, if we look into any of the clock tree, and if someone asks what is the level of buffering, so this is how you need to do is you need to calculate stage by stage. This is the first stage, this is the second stage, where your clock signal finally reaches to your destination. So it's basically the amount of stages that the clock signal has to cross when it is sent to reach its destination. So the amount of stages is equal to amount of levels. So it's as simple as that. Next, if you look into the next observation, let us try to look into the next observation of this. So in this case, this particular node A the capacitance that if this particular node A is driving is 60 femtofarads. Okay, and the next node, if you see the capacitance that the node B and C are driving, that is 50 femtofarads. So the observation over here that we see is each node is driving same amount of load. For example, if there had been even more clock trees over here, and we should be making sure that each and every node should be driving exactly same amount of load, and there are tremendous advantages of having this. So this is the base. This is very basic thing which usually is forgotten while building a clock tree. But this thing has got tremendous advantages on skew, on delay numbers, on many things. So we'll be looking into those in the later sections. So let me brief you about this. What happens if you have a same load over here? So what happens if you have a different load over here? For example, if you had 50 femtofarad over here, and if you had 40 femtofarads over here, so what can go wrong? So what can go wrong is the delay for this particular buffer will be different from the delay from this particular buffer. So in that case, if you see this particular path from this point to, let's say, this clock endpoint, and from this point to this clock endpoint, there will be a difference in the delay. And why there will be a difference in the delay? Because of this particular buffer driving a load which is 50 femtofarads, and this particular buffer driving a load which is 40 femtofarads. So basically, a delay of the buffer is, or delay of any cell in that matter, is a function of input transition and output load. That is the basic definition of delay for any standard cell on a circuit. In this case, if the output load is 50 femtofarads and this is 40 femtofarads, the delay will be different, and as a result of this, you will see a different, you will see a positive, you will see a finite skew between this and this points, or between this and this points. So basically, there is a clear advantage of having a same, or of having the same load at each node, having the same load at each node. So that directly impacts the skew number. Now the third and important observation is that at every level, if you see level 1, so let's say this level 1, the type of buffer is, let's say, buffer X. The type of buffer in level 2 is, let's say, it's Y. So this is also Y and this is also Y. So the observation is that at every level you should have identical buffers. So if the level 2 has got X buffer, the first buffer is X, the type of the buffer over here should also be X. It should not vary. So that is, again, there is a clear advantage of having this kind of scenario. So the advantage is that, again, the same thing. If you see a delay, so let's say there are two buffers. One is X, the buffer name is X, and the buffer name is Y. So buffer X will have a different delay table, and buffer Y will have a different delay table. So even though we will be meeting first two, for example, let's say this node is driving same load, which is 50 femtofarads. This node is also driving same load, which is 50 femtofarads. But the buffers are different. This is X buffer, this is Y buffer. So the delay table for Y is different from delay table for X. So in that case, what will happen? The delay that will be seen from this buffer and the delay that would be seen from this buffer will again different. That will again result into skew variations at this point. So you see how the advantages are very clear from this particular two observations. So these two are very important observations which might get ignored while building a clock tree, because things are very automated at this level of VLSI, and these are all like automated tools that do all this. But it's always a good check to do that at every level you have at every level each node should be driving same amount of load, and identical buffer should be present at every level. So you can see the clear advantage of having this thing. The clear advantage is, first, the very foremost thing is the skew. So having different buffers at the same level will create in different delay numbers. And the second one, having different output loads at the same level will create again different delay numbers. So the clear advantage is this is we'll be seeing a less variation in this queue. So basically there will be no surprises towards the end when you follow this particular so 2 levels of buffering. It's just an observation, but these are a clear these 2 points are a clear requirement of the clock tree. We can maintain, we can try, we should be trying to maintain at these 2 observations. It may not be always possible to do this, but it's always good to have these 2 points. So what we'll do is, with these observations, we'll try to conclude this slide, and from the next video onwards, what we'll do, we'll take the basic H tree that we had developed from in the videos in the past videos, and we'll try to create a buffer tree on this particular H tree also, on this particular H tree as well, and try to fill up the checklist again and see now at this point after buffering what are we meeting and what not are we meeting. So let us try to do all this from the next video. Thank you.